Welcome! In this session, we'll explore LeetCode problem number 700, search in a binary search tree. This problem challenges us to efficiently locate a specific node within a binary search tree, testing our understanding of BST properties and traversal techniques. Let's dive into the details and work through the solution together. In this problem, you are given the root of a binary search tree, or BST, and an integer value called val. The task is to search the BST and find the node where the node's value matches the given val. Once the node is found, you need to return the entire subtree that is rooted at this node. If no such node exists in the tree, you should return null. The input consists of the root of the binary search tree, where each node has three properties: a value, a left child, and a right child. The other input is the target value, val, which is the value you are searching for. The output will either be the subtree rooted at the node with the matching value or null if the value isn't found in the tree. To better understand the problem, let's look at an example. Here, the input root of the BST is represented as 4, 2, 7, 1, 3, and the target value val is 2. The structure of this BST is shown visually with 4 as the root node, having 2 as its left child and 7 as its right child. The left child of 2 is 1, and its right child is 3. When we search for the node with value 2, we find it in the tree. The subtree rooted at this node consists of the node 2 along with its left and right children, which are 1 and 3. This subtree, represented as 2, 1, 3, is returned as the output. Now consider another example where the input BST is the same, 4, 2, 7, 1, 3, but the target value val is 5. The structure of the tree remains unchanged, with 4 as the root, 2 and 7 as its left and right children, and so on. However, in this case, the value 5 does not exist anywhere in the tree. As a result, the output for this example is null, since no matching node with the value 5 can be found. In a third example, the input BST is again 4, 2, 7, 1, 3, but the target value val is now 7. The structure of the tree is the same as before. Here, the node with the value 7 is found as the right child of the root node 4. Since this node does not have any children, the subtree rooted at this node consists only of the node 7 itself. Therefore, the output for this example is 7, representing the subtree that is rooted at the node with value 7. The constraints for this problem specify that the tree can have between 1 and 5,000 nodes, and the values of the nodes and the target value will be integers in the range of 1 to 10 million. The tree is guaranteed to follow the binary search tree property, meaning all values in the left subtree of a node are smaller, and all values in the right subtree are larger. Some important edge cases to consider include when the tree contains only one node, where you should return the root if the value matches or null otherwise. If the value does not exist in the tree at all, you return null. Finally, if the value matches the root node, then the entire tree is returned as the output. To solve the problem of searching for a given value in a binary search tree, we need to consider the most effective way to locate the node where the value matches val. One possible solution is the brute force approach, which involves treating the binary search tree as a regular binary tree and performing a linear traversal. This can be done using either depth-first search or breadth-first search. The idea here is simple: traverse every node in the tree and compare its value with val. For implementation, we could use a stack for depth-first search or a queue for breadth-first search. However, this approach has significant drawbacks. The time complexity is O(n), where n is the number of nodes, because we might have to check every node in the tree. Additionally, the space complexity can also reach O(n), in the worst case due to the storage requirements of the stack or queue. Importantly, this method fails to take advantage of the binary search tree property, where the left subtree contains smaller values and the right subtree contains larger values. As a result, it is inefficient compared to more optimized methods. A more efficient way to solve this problem is to use the binary search property of the BST to guide our search. The binary search approach begins at the root and compares val with the current node's value. If val is less than the current node's value, we move to the left subtree. If val is greater, we move to the right subtree. If we find that val matches the current node's value, we return the node. And if we encounter a null node, this indicates that the value is not present in the tree. This approach can be implemented recursively or iteratively. The iterative method is generally preferred because it avoids the additional space overhead of the recursive call stack, making it more space efficient. When analyzing complexity, the time complexity of this approach is O(h), where h is the height of the tree. For a balanced binary search tree, this results in O log n, which is significantly faster than linear traversal. However, for an unbalanced tree, the time complexity could degrade to O(n). In terms of space, the iterative version has a constant space complexity of O(1), while the recursive version requires O(h) space due to recursion. The optimized approach, which uses binary search on the BST, is the most effective strategy for this problem. By leveraging the binary search property, we can minimize unnecessary comparisons and traversals, making the search process highly efficient. One key advantage of this method is its efficiency. At each step, the search space is halved, leading to a time complexity of O(h). This is a significant improvement over the O(n) complexity of the brute force method, especially for large and balanced trees. Additionally, the approach is conceptually simple and easy to implement, supporting both recursive and iterative solutions. When comparing the two, the iterative implementation is often preferred due to its constant space complexity, which makes it more suitable for handling larger trees. In contrast, recursion, while elegant, incurs additional space overhead due to the function call stack. Another important consideration is how this strategy scales. It performs exceptionally well for balanced trees, and even for unbalanced trees, it still provides acceptable performance, albeit with degraded time complexity. Overall, the optimized approach is faster and more robust than the brute force method, making it the clear choice for solving this problem. For this tutorial, we will focus on the iterative implementation to maximize efficiency and scalability for larger inputs. To solve the problem of searching for a specific value in a binary search tree, or BST, we start by understanding the unique properties of this data structure. In a BST, all values in the left subtree of a node are strictly less than the node's value, while all values in the right subtree are strictly greater. This organization allows us to efficiently narrow down our search by comparing the target value to the current node's value as we traverse the tree. The recursive approach leverages these properties effectively. The base case is simple: if the current node is null, it means the value doesn't exist in the tree, so we return null. Otherwise, we check the current node's value. If it matches the target value, we return the current node and the subtree rooted at it. If the target is less than the current node's value, we recursively search the left subtree. This recursive narrowing down process ensures that we only explore the parts of the tree where the target value could possibly reside. On the other hand, if the target value is greater than the current node's value, we limit our search to the right subtree by recursively calling the function on the right child. Now, instead of recursion, we can also use an iterative approach to achieve the same result. This method avoids the overhead of function calls by using a while loop to traverse the tree. We start at the root and continue looping as long as the current node is not null. At each step, we compare the target value with the current node's value. If they match, we return the current node. If the target is less than the current value, we move the pointer to the left child, and if it's greater, we move to the right child. If we exit the loop without finding the value, it means the value doesn't exist in the tree, so we return null. The efficiency of both approaches lies in the BST property, which allows us to eliminate half of the remaining nodes at each step, resulting in a time complexity of O(h), where h is the height of the tree. For balanced trees, this is logarithmic, making the search very efficient. However, we must handle edge cases, such as when the tree is empty or when the tree is skewed to one side, as these can impact the performance and correctness of the algorithm. Let's now examine the data structures and the computational complexity of our solution. Each node in the binary search tree contains a value, a pointer to its left child, and a pointer to its right child. For the recursive approach, the recursion stack handles the function calls as we traverse the tree. In contrast, the iterative approach operates directly on the tree without additional data structures, making it more space efficient. In terms of time complexity, both approaches run in O(h), where h is the height of the tree. For a balanced tree, h is proportional to log n, making the search very fast. However, in the worst-case scenario of a completely skewed tree, the height becomes n, and the time complexity degrades to O(n). For space complexity, the recursive approach requires O(h) space due to the recursion stack, while the iterative approach uses O(1) space, as no extra memory is allocated. With these insights, let's look at a Python implementation of the recursive approach. The function begins by checking if the root is null. If it is, we return none. If the root's value matches the target, we return the root. Otherwise, we decide whether to search the left or right subtree based on a comparison between the target value and the root's value. In the iterative solution, we begin at the root node and repeatedly compare the target value with the current node's value. If they match, we return the current node. If the target is less than the current value, we move to the left child. If it's greater, we move to the right child. This process continues until the value is found or the current node becomes null, indicating that the value does not exist in the tree. By avoiding recursion, this approach eliminates the extra memory overhead of a recursion stack, making it an attractive choice for scenarios where memory usage is a concern. With both the recursive and iterative methods, the algorithm efficiently leverages the BST property, ensuring that the search is performed in optimal time. These implementations provide a clear and structured way to solve the problem of searching in a binary search tree, balancing simplicity and efficiency. This solution implements a recursive approach to search a value in a binary search tree, BST. The treeNode class defines the structure of a node in the tree, while the searchBST function performs the search. The algorithm leverages the BST property where all values in the left subtree are smaller than the root, and all values in the right subtree are larger. 1. Base case, the function first checks if the root is none or the root.val matches the target value val. If either condition is true, it returns the current root node. This handles the scenarios where the search ends, either by finding the value or exhausting the tree. 2. Recursive search, if the target value is smaller than the current node's value, the function recursively searches the left subtree, root.left. This is because, according to the BST property, smaller values are always located in the left subtree. 3. Right subtree search, conversely, if the target value is larger than the current node's value, the function recursively searches the right subtree, root.right. Larger values are always in the right subtree. This approach ensures that the search is efficient, operating in O(h) time complexity, where h is the height of the tree. In the best case for a balanced tree, this is O log n, and in the worst case, completely unbalanced tree, it becomes O n. The space complexity is O(h) due to the recursive stack. This concise implementation effectively solves the problem while maintaining clarity and efficiency, adhering to the constraints and properties of a binary search tree. Here, we start by defining the treeNode class, which represents a single node in our binary search tree. Each node contains an integer value, a reference to its left child, and a reference to its right child. We provide three constructors, a default constructor, one that initializes the node with just a value, and another that initializes the node with a value and pointers to both its left and right children. Next, we define the solution class and the searchBST method. This method takes two parameters, the root node of the tree and the target value we want to search for. The first thing we handle is the base case. If the root is null, meaning we've reached the end of a branch without finding the value, or if the current node's value matches the target value, we simply return the current node. This ensures we either terminate the search or return the node containing the target value. If neither of these conditions is met, we proceed to decide where to search next based on the value of the current node. If the target value is smaller than the value of the current node, we know that in a binary search tree, smaller values are always located in the left subtree. Therefore, we recursively call the searchBST method, passing in the left child of the current node as the new root. On the other hand, if the target value is larger than the value of the current node, we search in the right subtree by making a recursive call to searchBST with the right child as the new root. This way, we navigate through the tree by leveraging its inherent ordering properties, efficiently narrowing down the search space at each step. Once the target value is found or the search terminates, the method will return either the matching node or null if the value doesn't exist in the tree. To begin, let's walk through the first example where the target value is found in the tree. The input binary search tree has 4 as the root, with 2 and 7 as its left and right children, respectively. The left child of 2 has further children, 1 and 3. the target value we are searching for is 2. The algorithm starts by calling the function with the root node, which has a value of 4. Since the target value, 2, is less than 4, the binary search tree property tells us to move to the left subtree. This leads to a recursive call where the root is now the node with value 2. Here, the current node value matches the target value. Therefore, the algorithm returns this node, effectively returning the subtree rooted at 2, which includes its children 1 and 3. Next, we examine the final output for this example, which is the subtree rooted at the node with value 2. This subtree contains the node 2 as its root, with 1 as the left child and 3 as the right child. Transitioning to a second example, let's now consider a scenario where the target value is not present in the tree. The input binary search tree remains the same, but this time, the target value is 5. Since 5 does not exist in the tree, the algorithm will traverse the tree fully as needed until it determines that the value is not found. For this second example, the algorithm begins by calling the function with the root node, which has a value of 4. Since 5 is greater than 4, the binary search tree property directs us to search in the right subtree. A recursive call is made with the right child of 4, which is the node with value 7. At this point, 5 is less than 7, so the search proceeds to the left subtree. However, the left child of 7 is none, indicating that we've reached the end of a path without finding the target value. The algorithm returns none at this point, signifying that the value 5 is not present in the tree. The final output for this example is simply none. Now let's consider a third example where we are searching for the root node itself. The input binary search tree remains the same, and the target value is 4, which matches the value of the root node. The algorithm starts by calling the function with the root node, and since the current node value is equal to the target value, the algorithm immediately identifies the target node. No further recursion is needed. The function returns the entire tree rooted at the node with value 4, which includes all the original nodes, 4 as the root, 2 and 7 as its children, and 1 and 3 as the left and right children of 2, respectively. In summary, the search algorithm takes advantage of the inherent properties of a binary search tree, where values in the left subtree are smaller than the root, and values in the right subtree are larger. This allows the algorithm to branch left or right based on a simple comparison between the target value and the current node's value. Recursive calls continue until either the target value is found or a none node is reached, which indicates that the value is not in the tree. The time complexity of this approach is O(h), where h is the height of the tree. This makes it especially efficient for balanced trees, as the height is minimized in such cases. When analyzing the time complexity of the search BST algorithm, it is important to consider the height of the binary search tree, denoted by h, as well as the total number of nodes, represented by n. In the best case, the target value val is located at the root of the tree, allowing the algorithm to terminate immediately with a time complexity of O(1). In the average case, when the tree is balanced, its height is proportional to log n. This means the algorithm will typically need to traverse about log n nodes to either find the target value or determine it does not exist, resulting in a time complexity of O log n. However, in the worst-case scenario, the tree is unbalanced, resembling a linked list. Here, the height of the tree equals the total number of nodes, n, and the algorithm may need to visit every node before reaching a conclusion. Thus, the worst-case time complexity is O(n). The space complexity of the search BST algorithm is determined by the recursion stack used during the traversal process. In the best case, where the target value val is found at the root node, no recursive calls are made, and the space complexity is O(1). For a balanced binary search tree, the height of the tree is proportional to log n, and the recursion stack will reach a maximum depth of log n during the search, leading to a space complexity of O log n. On the other hand, in the worst case of an unbalanced tree, where the structure resembles a linked list, the height of the tree becomes equal to the total number of nodes, n. As a result, the recursion stack could grow to a depth of n, giving a worst-case space complexity of O(n). Comparing this optimized approach to a naive one highlights its efficiency. A brute force search in a binary tree, such as using BFS or DFS, would involve traversing all nodes without leveraging the properties of a binary search tree. This results in a time complexity of O(n) in all cases. In contrast, the search BST algorithm takes advantage of the inherent structure of BSTs, where values in the left subtree are smaller and those in the right subtree are larger than the root. This property allows the algorithm to eliminate half of the tree at each step on average, reducing the time complexity to O log n for balanced trees. Mathematically, the number of recursive calls corresponds to the height of the tree, h. For balanced trees, where h equals log n, the average time complexity is O log n. However, in skewed trees, where h equals n, the time complexity becomes O n. This demonstrates how the algorithm efficiently optimizes searches in balanced binary search trees. When working with binary search trees, there are a few common mistakes to watch out for. First, forgetting to handle edge cases can lead to runtime errors. For example, the tree might be empty, or the value you're searching for might not exist in the tree. Always make sure your implementation accounts for these scenarios. Another mistake is unnecessary traversal. A binary search tree allows you to eliminate one entire side of the tree at each step, so continuing to explore both subtrees after determining the correct direction violates the BST properties and adds unnecessary overhead. Additionally, confusing comparison logic is a frequent issue. For instance, if you accidentally use the wrong comparison operator, such as checking if the root value is greater than the target when it should be less, it can completely derail your traversal. Lastly, modifying the tree structure, like reassigning root.left or root.right without justification, can lead to unintended consequences. Since this problem is search-only, ensure the tree remains unchanged during your implementation. Now, when converting a recursive approach to an iterative one, inefficiencies can arise if you don't carefully manage the stack or properly define loop termination conditions. This can result in infinite loops or stack overflows, so always validate your iterative logic. In interviews, there are also a few key points to highlight. Emphasize how the properties of a binary search tree allow you to eliminate half the tree at each step, resulting in a time complexity of O, h, where h is the tree's height. Be prepared to discuss the trade-offs between recursion and iteration as well. While recursion is simpler, it uses stack space, whereas iteration is more memory efficient and often preferred in production. Interviewers will also appreciate your awareness of edge cases, like empty trees, single-node trees, or when the value isn't present. Finally, be ready for follow-up questions. For example, they might ask how you'd search for the closest value to the target or adapt your approach for a general binary tree. This is a great opportunity to demonstrate your adaptability and problem-solving skills. Next, let's consider related problems and alternative approaches. Several other LeetCode problems build on similar concepts, such as inserting into a binary search tree, problem number 701, deleting a node, number 450, finding the lowest common ancestor, number 235, or validating a binary search tree, number 98. Practicing these can deepen your understanding of BST operations. Regarding approaches, the recursive method is simple and elegant, leveraging the natural structure of the tree, but it does require additional memory for the recursive stack. Both its time and space complexity are O, h, where h is the height of the tree. On the other hand, the iterative method avoids recursion by using a while loop, making it more memory efficient. The time complexity remains O, h, but the space complexity drops to O, 1, since it doesn't rely on the call stack. Choosing the right approach depends on the problem requirements and constraints. Finally, let's discuss key trade-offs. When deciding between recursion and iteration, consider the tree's depth. Recursive solutions are easier to write and understand but can cause stack overflow if the tree is very deep. Iterative solutions, while slightly more complex to implement, are more robust for production use and avoid this risk. Another consideration is how the BST handles duplicates. If duplicates are allowed, you may need to adjust your logic to decide which branch to traverse when encountering a value equal to the target. Additionally, the tree's balance plays a significant role in performance. For balanced trees, the height h is logarithmic in relation to the number of nodes, ensuring efficient operations. However, for unbalanced or degenerate trees, the height can approach n, leading to worst-case performance. In such cases, balancing techniques, like AVL or red-black trees, can be mentioned as a way to optimize the tree structure. Understanding these trade-offs will help you make informed decisions and demonstrate your depth of knowledge. Great job! To recap, we tackled LeetCode problem number 700, using the properties of binary search trees to efficiently locate a target value. We reviewed both time and space complexities, highlighted key takeaways, and discussed when this approach is useful. Keep coding, stay curious, and thanks for watching. Until next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!